this one, you see that it's the kinetic energy and this are related by the same quantity. That is negative. Okay, this they are related by the same quantity. Okay, it's more or less like half of that. So in terms this negative one, this is like half of that. Okay, so it is like it's that's if you consider this negative, and this is the half of the equation that we have here. It's just about that, right? So in essence, you see, this is like half in terms of number, not considering the sign. This is like twice. So potential energy is like twice the kinetic energy, right? So that's it. Now let's just briefly go over again so that we recap this portion. This part is very important. Let's get to the concept very well. There's a recap. So we started with the witness. We said we have this at the surface of the Earth, this Earth with radius RE. Now there's a satellite here. Okay. Now that also has radius R. Okay, and it's also revolving. So by virtue of this height, due to the height, it has potential energy. So there's a potential energy here, and it is moving, so it has kinetic energy. Right? Good. We can decide to find it moving from here to this point, the energy spent. That is the differences between the potential and the potential here or the potential energy. So the potential here and potential here, potential energy here. If you subtract that to give you the energy from here to here. Now we are not interested in the energy between this and that. We are interested in the energy possessed by this satellite in orbit. So the total energy in orbit will be equal to your PE plus your kinetic energy. Okay? Now by definition, if we want to define the PE of anything, we define it from infinity, and we say infinity is 0. Okay? So all the potential below it will be negative. Right? Because we have chosen by reference for the infinity to 0, all potential below it will be negative. Of course this is higher, so if you are below it, then you will be negative. That is the reason. If we take the Earth as reference, then it becomes something different. Right? So the potential at this point here would then be what? Negative G M N R. Remember we said potential is equal to what? Work done over what? Mass. Okay? That's potential. So we know work done, work is equal to force times distance, which is force is what? J M R squared times distance, which is R. Okay? So if we put this one here, J M over R squared times R, all divided by M per M. Okay? Right, that will be the potential. But if we want the energy, then we have to multiply by the value that we have here. Right, so work done, this is the work done times distance. So this is the work done is the same as potential energy. But potential alone will just be, you divide by M. You divide by M. This is potential alone. If you divide by M, you're going to get Jm over R. Okay, but C is potential energy, so it is times M. But of course, with reference, it becomes negative. Because our kinetic energy is half mv squared. Now, we can get an expression for V in terms of Gm, so that the equation can be simplified. From that, we know centripetal force. As it's going around, there's a centripetal force. And that centripetal force is also the same force of attraction between the satellite and the Earth. That centripetal force is equal to is equal to mv squared over R. And then the force of attraction between the two is equal to Jm small m R squared. Okay? So we can say that mv squared is equal to Jm over R squared. Here is R. Okay, this is R squared. So this R will cancel 1. So that m will cancel m. So that we have what? M squared is equal to Jm over R. This is what we want. Now we can substitute here in V for V squared. We can substitute this one here. Then we get what? Jm R plus what? Half m Gm over r. So see that this m is here, Gm is here, m is capital, sorry, this is capital, and capital M is here, r is here. So see that in terms of numbers, this whole thing is like -1, and this is like what, half. So it's like the potential energy is like twice the kinetic energy. In terms of quantity, it's like twice the kinetic energy. And that's the picture I wanted us to show. Right, so at this point, we'll leave it as it is. Just a recap for the big six. The big six is important in physics so that you can actually get the concept very well. So from the big six concept, what we say the big six, what the big six. So the concept, the big concept summary, that will end us. So the first one we say the lines of forces or flux. Then the next one we say the density. Next one we say the intensity or strength. Then the next one we say potential. Then the last one we talk about force. The last, not the least, we talk about work done. Okay, this principle will guide us in physics a lot. So lines of forces, if it's magnetic, we have the flux like that. Okay, the density, you can have magnetic flux density. The rest will just be the lines of forces. If it is this a charged body, okay, two bodies attracting heavenly bodies, it's always force of attraction. So this over A becomes as the flux density for magnets, magnetic field. Now intensity means your force divided by your Q, or your force divided by your Q is your intensity. Okay, or let's say another expression, somebody can look at force over mass as a kind of intensity somewhere, but this one I'll put in better terms. This is it. Now potential is to do with work done over mass. So work done over mass, okay, over mass, okay. So whilst this one is to do with force, this is supposed to do with work done or energy. Okay, that's the difference. The first one, I think we overlapped that one and said distance. Okay, no, not distance, but we're looking at force for intensity. The force per is intensity. Work done per mass, or work done per charge will be potential. Okay, so we are looking at the potential. Now the force is what? It's given by the inverse square law, m r squared over q r squared. Okay, the work done is equal to force times distance. Okay, so whatever force that you have times your distance, which can be r in some senses. Okay, so if you have this concept in there, you can build upon it. Okay, so just remember intensity, we are looking at force. Okay, potential with reference to energy. Okay, the density is reference to the area, sometimes volume. Okay, and the flux is actually the lines of forces. Okay, the lines of forces. Now this will be a very good guide for all the other equations that we'll be looking at. Okay, so if I say find the equation for, let's say, electric field intensity. Okay, electric field intensity. We say force over Q, because we are dealing with charges. What's the force? Scale Q square. Okay, over charge. This becomes per unit charge, so it's a small charge we are talking about. Okay, right, so this comes out as Q over R squared, and it comes intensity. So that's a simple way to derive the equation. Right, so if I say find the potential at the point, the potential is usually given like this. The potential is what? Work done over what? The mass. Let's say potential for everybody. So the work done, what's the work done? Work done is force times distance. So it's the same as force times distance over m. Let's see how that will work out. So that you don't need to commit them to memory, and that will guide you. Okay, so here we're going to have the force is what? K M small m over r squared. That's the force. The distance. If it's moving the two to one surface, that's the distance r. Okay, all this over what? M. So what are you going to get? K capital M small m, r will cancel one m, and this m will cancel that. Okay, so this m goes off, and then we have only one r. The g here is the k here is always g, so it becomes g over r. This becomes potential, but potential energy is different. Potential energy, the potential energy, you have to multiply, but that's energy. So it is this potential per mass. Okay, so this potential times the mass, so it becomes g m and r. Have to be the potential energy. Okay, right. So if you have the potential, you multiply by the mass, you get the energy there. So that will be the energy per mass, because this potential is what energy per mass. So if you want the potential energy there, so then this potential per mass times the mass is given the energy. Right. Okay. So that is that. Okay. So this is the same, and the work done is the same as potential energy. Kinetic energy. So if I put it here, it's just potential. That's the principle. So get this very well, and then you are good to go with the others. So we'll draw the curtains here before we move on to the next chapter on electricity and then electric current. Right.